Well, good evening and welcome to UW Space Place. Tonight, as our guest speaker, we have John Chisholm from the UW Astronomy Department. John is actually a native of Madison, went away to college, and then came back here to get his PhD in astronomy. He's studying galaxy evolution, and tonight is going to tell us about how galaxies get old, why galaxies can't last forever. John?
Well, thank you, Jim. Well, thank you guys for being here. And like Jim just said, my name is John Chisholm, and I will be talking to you tonight about why galaxies get old and what makes galaxies become old. But first, I'm an astronomer. I'm a graduate student in my 6th year now. It seems like it's been quite a long time, and it kind of has. But by and large, whenever I meet someone and I tell them that I'm an astronomer, the first initial reaction is, "Oh, that's so cool. That's so great. I've never met an astronomer before." And then the second question is always, "What do you do with that?" And when I was younger, I'm more mature in my older age now. When I was younger, I was thrown off by that question because does a firefighter get asked what they do? Does a banker get asked what they do? Like the first thing when you meet someone is a firefighter, like, what do you do? Like, I go into burning buildings and I save people. That's what they do. I guess everyone knows what that is. And unfortunately, I think the preconceived notion of what an astronomer is these old-timey pictures where you have people that are looking through the backs of telescopes here. They're gazing at stars. They're trying to understand what they're looking at. And unfortunately, I think we as astronomers have not updated that image of what astronomers do. And we've left the general public in this state of, how do you be an astronomer? And that's really unfortunate because in the past 25 years, or in my case, 27 years, I'm 27 years old. In the past 27 years, we've really been in a golden age of astronomy research. And we have encountered completely new challenges and uncovered vastly important clues of the origin and the evolution of the universe as we know it. And by and large, that is thanks to some of the telescopes that I will be talking about tonight that are on your screen, like the Hubble Space Telescope, orbiting in space around us. It's a fantastic telescope that's produced some very deep images and spectroscopy of the universe. But some lesser known spacecrafts that I'm going to be talking about, New Horizons. Everyone's kind of heard about New Horizons recently. It's been in the news, but it's fantastic. WMAP. WMAP is a telescope maybe not a lot of you have heard about, but it has actually produced probably the most impactful result of my lifetime. And I'll talk about that in a second. But also the Sloan Digital Sky Survey. And this is a telescope in New Mexico that the University of Wisconsin is actually very intimately related to. And it is the most cited telescope in astronomy. And by and large, the general public probably doesn't know what the Sloan Digital Sky Survey actually is, but it has revolutionized astronomy in the past 28 years. Further, really, technology has made it so that in the past 28 years, or my lifetime, you can really understand the fundamental physics that's going on in the universe. When you couple that with really hardworking astronomers, as you see down here on the right, you get new ideas about what is going on in the universe. And so before I go into my research, I kind of want to hit on 3 highlights of major astronomical accomplishments that have happened in the 27 years that I've been alive. These 3 accomplishments are nowhere near all of them, or maybe not even all of the important ones, but there are some that I think are pretty cool that I really want you guys to be aware of. So 2015, I think, should go down as the year of Pluto. And if you guys are not aware, in 2006, we sent a spacecraft to go from the Earth to Pluto, which is a distant planet that is more than 400,000 miles away. And to just think that we as humans put together a spacecraft that is venturing out to the far reaches of our solar system is pretty incredible. But on July 15th this past year, New Horizons, the spacecraft, actually reached Pluto. And it is sending back more fantastic science than we ever imagined it probably would. So on the left here is a picture of Pluto. And one thing that scientists really started to notice right away is that the terrain is fantastically different across the planet. This kind of heart-shaped feature here went all over social media. People were saying, Pluto loves us, everyone's happy. But what is fantastic about this image is that it really gives so much high level of detail about what's going on in the outer part of our solar system that we never knew. For example, if you look very closely at this image down here, you can see some faint fuzziness around the actual surface of Pluto. And that is an atmosphere of gas around Pluto that we never expected to happen. Pluto is smaller than our moon. Pluto is very small, and yet it's able to retain this atmosphere. Another really fantastic part is these up-close images. So these are scales of miles. And this looks like you're flying over the Rocky Mountains or something like that. But we see mountains on Pluto. And these mountains are made of ice. So tonight, it's January, and there's ice all around us when we go outside. But on Pluto, ice is actually able to form out of CO ice, so carbon monoxide ice. So this is carbon monoxide ice, and these are mountains of water ice that have been pushed up out of this carbon monoxide down here. And fantastically, if you zoom in on this area down here, you see that this smooth surface is actually granulated. And what we've discovered is that beneath the surface of this ice is actually convection that is taking cold ice and moving it down to the bottom of the ice and bringing warm ice up with it. So we actually have an active layer of ground on Pluto, something that no one in their right mind ever expected to find in the outer surface, or the outer solar system. But Pluto is able to regenerate its surface much like volcanoes regenerate the surface on Earth. And what is great about New Horizons is that we are just touching the surface of the data. The data hasn't even all been sent back to Earth. So they've been slowly trickling back the data, and we're only about a third of the way through actually even receiving the data from New Horizons that it measured on Pluto, let alone trying to understand it. So we have a fantastic amount of data on Pluto. So another really great thing that astronomers have done since 1988, when I was born, is that they have been discovering planets well outside of our solar system. So in 1988, there were 0 known planets outside of our solar system. All we knew were the 8 planets that make up our solar system. Pluto was a planet back in 1988, but now it's not. And since 1988, we have been really devoted to finding planets orbiting around other stars, or so-called exoplanets. And so in those 27 years, we have discovered 1,930 planets that orbit stars that aren't our sun. That's fantastic. And more than half of those have been thanks to one spacecraft called Kepler. Kepler is a spacecraft that orbits Earth that is solely devoted to finding planets. And the holy grail of planet science is finding what are called habitable planets. So life as we know it requires water. And in order to have water, a planet needs to be a very precise distance from its star. And we call that distance the habitable zone. And so Kepler has actually found almost 300 planets that orbit around their stars in which liquid water can exist on the surface of those planets. And now that we've found these habitable planets, we're trying to find Earth-sized habitable planets. So a planet that is the same distance from its star as Earth and the same size as Earth. And so we're really looking out into our galaxy and trying to find things that mimic what we know and who we are. And I think that in the next year or two, you will see a planet that is the same size as Earth, but orbiting around a different star. And finally, what I think is actually the biggest scientific discovery of my lifetime is now we actually know what makes up the universe. And you might, when you think about that, that might sound a little strange for me to say, because I know what this podium is. I know what this laptop is. They're atoms. They are composed of things that we are familiar with and we have seen since the day we were born. We see it through light, which are photons, which we've seen since the day we were born. And you would think that that's the universe. But it turns out when we take an image of the extremely early universe, which is what we did with WMAP, and we have done since then with a satellite called Planck, we can actually image the universe when it is infinitesimally young, so about 400,000 years or so. And we're able to capture the light from this very, very young universe. And what we have found is that the clustering, so how congregated these little light points are here, actually will tell us about the composition of the universe. And it's surprising that we found that the atoms that make up you and I, make up everything around us, are only about 5% of the actual universe. The 25% of the rest of the universe is something called dark matter. We don't know what dark matter is, but we know it must exist. It's matter that interacts gravitationally, just like the Earth is keeping you to the floor through gravity. Dark matter interacts with other dark matter through gravity. Even more exotic is this other term of energy called dark energy. Makes up 71% of the total energy and mass within the universe. And we have no idea what it is. But we know it must exist from this incredibly precise map of the very early universe. So there's a lot of studies that are trying to figure out what dark energy is and what dark matter is, so we can better understand parts of the universe that we just can't see and we can't feel. But those are ongoing research within astronomy and within physics to try to better understand our universe around us. So now I'm going to start, one more thing. None of these discoveries, none of them, could be possible without you guys, without everyone that's listening, without the taxpayers that have generously supported the NSF and NASA. So I think that as astronomers, we really want to thank you for your support. And we really want you to know that we are working as hard as we can to try to uncover these mysteries. And we're very appreciative for what you have done. So to get into my research, I study, like I said, what makes galaxies age. But first of all, what is a galaxy? So this is an image of one of the nearest big galaxies to us called the Andromeda Galaxy. And galaxies are these large collections of gravitationally bound stars and gas. So gravitationally bound, what does that mean? That means that gravity, the same thing that's holding me to the ground, is holding all of these stars in this galaxy together. Same with the gas, the same with all of the dark matter and everything else within this galaxy. So it's a gravitationally bound system. There are two main components of galaxies that I'm going to be talking about. The first is stars. And stars are really the backbones, the flesh of galaxies. They are what emits the light that lets us see what galaxies are. And for example, on the right here is the sun, the star that we know best. And the Andromeda Galaxy has over 1 trillion stars gravitationally bound within it. That's a fantastic amount of stars within one area. And this is really what creates what we see as a galaxy. A couple times in the little bit here, I will be talking about how massive something is. And masses in astronomy are really hard. Like I weigh 185 pounds. That's something you can understand. But when you have a galaxy that has 1 trillion stars within it, the masses start to get a little bit too many pounds to really go in there. So what we usually do is we do it in units of solar masses. So the Andromeda Galaxy is about 100 billion, weighs about 100 billion solar masses. So there's 100 billion sun's mass within this Andromeda Galaxy. So I said that the stars are the flesh, the bones of a galaxy. There's another component that is really important to the story, and that is the gas within galaxies. And you're pretty intimately familiar with gas. You're breathing it in constantly. You're smelling it. You're living off of gas. And galaxies contain a large amount of gas as well. The main gas within galaxies is atomic hydrogen. So that's 1 proton, 1 electron. And the Andromeda Galaxy, it had over 1 trillion stars. This galaxy has 7 billion solar masses worth of gas. So a lot less gas than stars, but still quite a large amount of gas. I think that we can agree with that. But what's interesting is that the kind of picture that you paint when you look at the gas within the Andromeda Galaxy is that it's distributed very differently than the stars. So you have this fantastic ring-like structure within the Andromeda Galaxy, whereas you have stars all the way through the galaxy. So these points of light, they're stars, and there's no real stars within the gas. And the gas and the stars are intimately related, as we'll talk about in just a little bit. Galaxies are everywhere. This is what's called the Hubble Deep Field. It is the deepest image that we've taken with the Hubble Space Telescope. And everywhere we look, every single place we look, we find galaxies. So with the exception of this bright star right here, which is in the Milky Way galaxy itself, all of these points of light are galaxies. Some are very close, some are very, very far away, and that makes them seem much smaller. But we have a countably infinite number of galaxies in the universe. And everywhere we look, we see them. It's a fantastic image that you can just always see some very fun galaxies. And what's great is that you start to notice that every galaxy has its own characteristics. This galaxy right here doesn't look the same as this one, or the same as that one, or the same as this one. They all have their own fingerprint, their own identity, their own flavor as you go through it. And so we can start to look at different types of galaxies, and we can say, why? Why do we see some galaxies that are, weirdly shaped, kind of rectangularly shaped, some galaxies that look like they've just exploded upon themselves. This galaxy right here is called the Cigar Galaxy because it has this cigar shape here, but then it has wisps of smoke coming off of it. Another one is, again, the Andromeda Galaxy, which is very close to the Milky Way, which is the galaxy we live in, and we think looks pretty similar to the Milky Way that we live in as well. And finally, we get these weird ball-shaped galaxies. They're just spherical. They're very distant, and they just look strange. So what causes these very different types of galaxies? That's another question that we want to really be asking. And so now I'm going to get a little personal, and it's going to be a little embarrassing at times, but I'm going to go on a side tangent real quick. So humans, we're pretty intimately related with humans. You know, we know each other pretty well. And humans grow too. So humans grow. We start out as these little babies. This is me at some age. And we eat, in this case, I think it's a Rice Krispie treat. We eat, we make a mess, we sleep, we eat some more, we do some exercise, we grow. We start from 8 pounds and we grow up to 180 some odd pounds. And how does that happen? Well, we consume food. We grow bones, we grow muscles. We really turn that energy or that food that we consume into us, into what we are, into who we are. And so that's how humans grow. How do humans age? Well, here's an example, another personal example of me in the center right here. And this is my dad and my grandfather. And while we have a lot of the same genetic makeup, there's a large difference between the three of us because we're at different stages of our lives. I have, at this point, not grown as much as my father. I have not aged as much as my father. Whew. I have not, and my grandfather is different. And it's an inescapable fact of life that we age. Ever since Ponce de Leon and people before him, we have been looking for this mythical fountain of youth. We don't want to age. We want to stay just like we are at some stage of our lives. Everyone has their own stage that they would always like to be, but we do. We do, and we age. And so how do we study aging in humans? Well, there's a couple ways that we do it. One, we can just look at humans. So again, we can look at me, we can look at my father, and we can look at my grandfather and say, what has changed between these three people? What has changed? Well, as this little child gets older, his voice gets deeper, he gets facial hair, he starts losing hair in some places and gains hair in others, and he gets bigger. He starts getting, muscles, and then he'll start getting smaller. It's kind of a weird aging process, but we can look at people, we can observe them, and we can say with pretty high fidelity what the actual impacts of aging are. Another thing we can do is we can actually take blood. We can look at cells. We can use microscopes to get to the molecular level of humans, and we can say, oh, there's testosterone that's released during puberty, and that's what brings about a lot of the aging processes in teens. And we can then look and see what happens to cells as people get even older, and we can understand the aging process by actually manipulating the blood and the cells of humans. And that has really helped us progress in the topic of aging. It's still actually a very hard process to understand in humans. And as some of us know, we still get old. We still don't know what causes the aging process to happen. And it's something that we still are doing active research in the medical field to understand. So galaxies and humans actually, the way that we study their aging is actually fairly similar. So in order to study how galaxies age, we observe them. We observe many different types of galaxies, and we try to say, well, this one's young, this one's old. There's maybe some sequence that progresses to change the young ones into the old ones, and we make hypotheses like that. It's very similar to looking at me, my father, and my grandfather, and seeing the differences between us and trying to make some hypothesis of what really brings about that change, what brings about the aging process. The second way we can do it is we can do physics, math, and galaxy simulations on our computer. So it's very similar to looking at blood and cells within humans and saying what brings about the change within the cells. we can do the same thing on our computer. So we can create a galaxy on our computer with physics that we think we know, and then try to see if that matches reality, and kind of go back through the whole process iteratively and say, what are we missing? What did we forget? What did we leave out? What do we need to add in order to make the galaxy within our computer look like the galaxy that we observe? So those are the two main paths that we're going down. And physics has really helped us a lot. We've really gained some great insights into what happens to grow a galaxy. So, like I was saying before, the backbone of galaxies are stars. And stars are actually formed out of gas. So what happens to form a star is you start with this giant cloud of gas. And gravity is this force that always wins. You can't escape gravity. It's kind of like the tax man. You can't escape the tax man. You can't escape gravity. Gravity is always going to win if you give it enough time. So what gravity will do is it will eventually compress this large cloud of gas into a smaller and smaller region, which will heat up the temperatures of the gas and give the gas more energy. And eventually, what's going to happen with the gas is it's going to have so much energy that when it slams into another gas particle, it's going to stick. And when it sticks, it's going to release a little bit of energy, and that's going to heat up the gas a little bit more. And this whole process is going to keep on happening until there's so many collisions and so many sticking processes that the cloud now becomes a star. And so that is kind of the process in which gas is converted into stars. And of course, plugging recent observations, this is a fantastic observation that was made in the year 2015 as well, where we are observing a protostar in the center. This is a star that has not quite had that sticking process continue. So it's not quite a star, but around it are these little regions, these little cleared out regions. So there's gas all over here, but there's these little clear regions right here. And what we think that is that's planets forming around a star. And that's fantastic because you can compare it to something like a mock solar system that we know, and really this doesn't look too dissimilar. So we're viewing a star just forming in this image, which is absolutely incredible. And we're viewing the planets that are forming with it. So stars are born, but unfortunately stars also die. And the lifetime of a star depends on how massive that star is. So more massive stars, they live, they party harder, and they die sooner. The good always die young. The massive always die young as well. So the massive stars will actually die before the low mass stars. And that allows us to actually age date the galaxies around us. So this is the first way that I'm going to talk about how we can actually age date galaxies. So we look at galaxies and we look at the stars within them and we say, this galaxy right here, this galaxy is very young stars. And that means that the stars must have formed very recently because young stars, high mass young stars, die very quickly. Okay? And that allows us to kind of say that these galaxies are young, these galaxies are adolescent, these are in their middle-aged, and these are very old because they have no high mass stars left in them. So they haven't formed stars very recently. So by using the ages and the masses of stars, we can get at the ages of galaxies. And that's great. But there's a problem. I've painted this whole This whole picture of how gas converts into stars, and that's kind of how we build up galaxies. We get big and strong by munching on all this gas that's in our galaxy. But if we look at the gas that will form stars within, say, Andromeda, we find that there's not enough of it to grow the backbones of these galaxies. And they must be dying very quickly. But we don't see a lot of dead galaxies around us. So we know that these galaxies can't be dying right now. There must be something that is feeding them. It must be something that is saying, here, galaxy, here's some more Rice Krispie treats for you to eat so that you can get to be big and strong. And what we have discovered is that there is this thing called the cosmic web. That is this web-like structure that is full of gas that connects the galaxies, which are these little dots. So these little dots are galaxies, and these little string-like structures are this web of gas. And it's a highway of gas that is feeding the galaxies. So when we look at a galaxy, we don't see enough gas to make the galaxy be as big and as strong as we know it will be. But that's because the food's still coming. Someone's still at the grocery store. Someone's still getting the Rice Krispie treats to feed to little me or little galaxy to make it be bigger and stronger in the future. So this is something that we've only uncovered in the past 10 or 15 years of a way in which we can actually keep feeding galaxies to make them bigger, to make them stronger, to make it so that they don't die as quickly. And another way we can look at galaxies is we can measure the amount of stars within galaxies. And we can say, okay, so we know that this galaxy is young, but how big is it? And it turns out that very young galaxies, by and large, are very small. So kind of like I started out very small, and I ate a lot of Rice Krispies, and I turned into a very big person. Very young galaxies start out very small, and they eat a lot of gas, and they go through some angsty sort of adolescent phase and turn into middle-aged galaxies that will eventually turn into old galaxies and completely stop forming stars. That's kind of the picture that we've been formulating recently. However, even this isn't enough to stop a galaxy growing at the rate we know it should. So we know this from observations, we know this from simulations. Both sources tell us that there must be something that is actually bringing about this change more rapidly. It must happen very, very suddenly. And so because of that, we've been looking for new ways in which to actually take away the food, to strangle or to starve a galaxy. And what we've come up with is that the high-mass stars, the very bright stars within galaxies, don't die peacefully. They don't give up their lives as being the backbones of galaxies very easily. And instead what they do is they explode as a supernova. These supernovas are very energetic explosions that actually can outshine a galaxy. So down here is an image of a very nice blue galaxy, and right here is a supernova. And this supernova is actually brighter than the entire galaxy. So these explosions impart so much energy into the galaxy that if you have enough of these explosions in a tiny area, it can actually shred the gas out of the galaxy and launch it many, many distances out of the galaxy. So this is an example. This is the Cigar Galaxy that I was talking about before. And in green and yellow here, right in here, are the stars within the galaxy. And this galaxy has had so many supernova go off in such a small region that it has ejected out its gas. It's basically gone on a hunger strike. It's been saying, I can do this no longer. I will throw my food away, and I will no longer grow, is what's going on. So this gas is just being ejected out of the galaxy. And by ejecting out your food, by ejecting out your ability to grow, the galaxy will actually stop growing. So the galaxy will then be left with no gas, no way to get bigger, no way to get stronger, and it will then just kind of age. It'll get older very rapidly. And so this is what I have been observing. I've been using the Hubble Space Telescope to look at very hot gas within those galactic outflows, as they are called. And I've been using the Atacama Large Millimeter Array, which is the newest and most amazing telescope array that we have built yet. It is in the mountains in Chile. And this probes the very cold gas within these galactic outflows. And using these two, I'm able to get a handle of how much gas these galaxies are throwing out, how much they're just getting rid of. And we're coming to the picture of understanding that these outflows are actually capable of doing what we thought they were. They're capable of throwing up their food and strangling themselves and going from a very young galaxy to a very old galaxy very rapidly. So the picture is that this ejection of gas, the fuel to make future generations of stars, is actually what transitions it to be something that's old. And it's very akin to, this is me, it's very akin to the process that makes me transition to my grandfather. It's the age and the timing, that mechanism that has created this transition like that. So we're really starting to paint the picture of the physical mechanisms that are responsible for aging a galaxy, responsible for growing a galaxy. And this is really starting to coalesce the picture into a very coherent framework. And so that's all I have. Thank you very much for your attention. And I think we'll take questions now.